right, so welcome everybody to Stat 200. This is supposed to be a second semester course in statistical analysis. I know, raise your hand if you've never seen any statistics at all in your life, you know, before. You've never had any statistics. Raise your hand, I want to see. Oh, good. So most people here have at least had some exposure to statistics. I think you'll be okay because we're going to do some review exercises in the beginning. But if not, there's another Stat 200. I think it meets at 9 o'clock in the morning on Monday, Wednesdays, and Fridays. And you might want to check that out tomorrow on its first day, Wednesday, to see if that's more suited to your needs. Okay? So, today what we're going to do is we're first going to go over the basics, the syllabus, how to access the homework, how the grading is done, etc. And that will take some time. And then we're going to at least cover the first chapter in your notebooks. I see a lot of you have the notebook. I'm very happy about that. And maybe even get to the second chapter. Okay. So one rule I want to set, ground rule at the very beginning, is to please, it helps me if you ask questions, helps me a lot. I really, even though it's a big class, I want it to be more of a conversation. So raise your hand, and if I don't see you, please, class, help out and say questions, so I look up. And so, I mean, at any point, you can always interrupt me. It helps me know if you're interested in what you need to know. So starting right now, just raise your hand anytime, and please help out. I hope everybody feels free to ask any question. Okay? So let's begin by looking at the syllabus here. And how do you access? First of all, you access this page. Well, how would you get to it? What you would do is, let's open up a new window. This is really easy to remember. You say go.illinois. That's not a dot, that's a comma. go.illinois.edu/stat200. Okay? And that's the short URL that will take you right here. So this has all the course information. So you've got the syllabus here. We can look at quickly. So this is the best way to reach me. Our class time is, obviously you're here. This is there are two sections. One's in person, you guys, and one's online, and they're exactly the same. So the online people are going to be watching this video. Right now it's being filmed. And you're welcome to watch it too. I'll get to that in a minute. I'll show you where you can access that. So it's a synced class, in person and online. So the videos of our class will be posted on our calendar here about an hour after the class. So if you click on the calendar, you could click here or here, click on the calendar. And right now, there's no lecture here because it will take about an hour and a half after the class ends for it to be posted. But you'll see exactly what we're talking about now if you want to review. This is great for both the in-person. For you guys, it's great because you can't concentrate for 80 minutes straight, right? Who can? It's almost impossible. Nobody can. So anything you miss, and you don't have to worry if you have some questions or something, or you're not understanding something, you know that like in an hour you can just look at the whole thing again. So if you space out, and really, who is not going to space out? You can't concentrate for so long. So, so it's actually good. You can just, or if you miss a class or whatever. So what's the advantage of coming in class? The advantage for in class was great for me. It helps me teach, to have questions, to have an actual live audience. And I hope it's great for you too. You can ask questions and you'll get iClicker points for coming, because I really want to encourage you to come. I think it's a great advantage we're in the midst of an experiment comparing, we're doing an experiment right now, which is really cool. I'll talk about that later, but basically it's comparing in-class education, you guys, to the online, you guys at home who are also watching this, right? All right, so here's the TA office hours. We have a big team helping out here, and I'll be there too, 4 to 6 every day in 23 Illini Hall. All right, so it's a great place to come and do your homework. If you have technical problems, experience any glitches, there's 2 tech experts. They're right here with me today. You want to stand up? This is David Collier right here. You'll be emailing him or Yuck Tung in the back. And we have an amazing tech team. It's great, so you'll get your questions answered right away. And David will usually be in the lab during these office hours. He'll usually be there as well. All right, so homework. All right. How many people, homework is done on LANCAPO. Raise your hand if you're familiar with LANCAPO. Oh, good. A lot of you know what it is. It's just how many people have taken Stat 100 with Carly? Where's Carly? She's right over there. Yeah, so this is a continuation of Stat 100. So if you've taken Stat 100 with Carly here, then I think you'll be a jump ahead of other people because we're doing the same methods. We work together. We're both involved in this experiment, so we both believe in the same methods of teaching by example and teaching with a workbook that I see many of you have. All right. So LANCAPO, we can go to it right now, and just so I can show you what's up there, it's where you're going to be doing your homework. So let's look at it, and you'll put in your net ID and your password, and log in. LANCAPO was going to grade you immediately. So as soon as so this is Stat 200 right here, you won't have all this. I should change it to the student view as soon as we log in so you can see. So we're going to switch role to the student. And what you should do is go to the contents page. And this is what you'll see right now. All right, so you can do this right after class. And if you're at home, you can do it right now with me. So you can look at what's due right now. Why don't we look at what the easiest thing to do right now is this bonus survey. So you can do that. And it's a way, statistics can be about anything. So I think teaching by examples is great. Getting involved in real data analysis is great, as long as the subjects interest you. What can interest you more than yourselves, right? So this is basic. We are all, you're coming from all different disciplines, right? You don't have a shared major, but we do share information about ourselves. So we can analyze ourselves and that makes it so much easier because we don't have to know the who, what, why, when of how the data was collected, the usual stuff, because we know how the data was collected. It's our own. So for example, so you just fill out this, it's anonymous, and you get credit for submission. Okay, so you can fill this whole thing out, and when you have to answer every question, and you will get credit, full credit, if you answer every question, but there's no way I can tell who submitted which answers. I can just see that you submitted. So it's really a fun way to analyze our own data. So we're going to have a number of these. So obviously, if you lie or tell stories or just do stupid stuff on here, you're just corrupting our own data, which is annoying for everybody. So please don't do that. The truth is much more interesting and often stranger than fiction. And it's what we want to know. That's what stats is about. All right, so that's the, let's go back to the contents. And the other thing that's up here that's super helpful, not just for people who haven't had stats, but for everybody, is these bonus review problems, which are the actual pre-lectures from the Stat 100 course. So if you've taken Stat 100, you've seen them. If not, this is a great way to prepare yourself for actually the very first few chapters in the notebook. So if you don't understand some of what we're doing today, when we start actually diving into the notebook, if you don't understand that, I bet these videos will help. So they're not only videos, they're videos, very short videos with questions. And you'll get bonus points for doing them. So there's basically 3 topics here, just what is a z-score, what is a probability histogram, there's Carly in the video, and what's the last one? I think the last one is significance tests. There she is again, the one sample z-test, which the significance test is where we start. We assume you know this stuff. If you don't, if you need review, go back and do these. They're due Friday, but do them as soon as possible. I can't stress that enough. That's where very first thing you should do. All right, so now let's go back, and what else is up here is then our homework assignment, the first homework assignment. So make sure you can get on here. If you have any problems at all and you can't get on here, send me an email or send David or Yuck an email, the tech specialist. So let's go back to our syllabus. And so our exam schedule, let's check that out. So there's 3 evening exams, and here's the schedule for them. And they're an hour and a half. And the reason I give them at night is so people won't be under any time pressure. If you're in the online section, you'll also be taking these same exams at the same time. So because 99% of the people online are here on campus. So we're all going to take the same exams together. Everything's the same for the 2 courses. Really, that's the point. I just feel like we should break down this artificial barrier between in-person and online. Our whole lives are a blend of the 2. Let's take advantage of all the technological tools that we have and learn however we can. So I also, those of you who are watching online, I strongly recommend you come to class sometime. You know, if you see a topic you think might interest you or you just feel like coming to class, we welcome you always. All right. Now the final exam is, you guys are lucky, Friday, May 4th, I think so. It's the first day, very first exam of exam period, so we can leave. I'm happy about it. I'll try to schedule the online people early too, but I have to work out with the university, and I'll tell you as soon as possible when your time would be. You'll have an option of a few times. All right, now, here's the real key, is this calendar. I want you to check it all the time. It has everything in it, and as I said, the whole course is going to be here, including the videos, the lectures. So you know when everything is due. Monday homework is due Mondays and Wednesdays at 11:59 p.m. on LANCAPO. All right, that's when it's due throughout the entire semester. And then sometimes there'll be bonus work due, usually on Fridays. So this Friday is the bonus work. And what's this? This is just review from old Stat 100 lectures. If you need additional review after doing these bonus review, then you can look at this. This will just give you more review. Okay, and here's our exams on here as well. So let's see if there's anything else that we need to know. So what is this compass being used for right here? Compass is being used to display your grades and for me to send emails to you from and post announcements. I'm sorry, there's 3 websites I've talked about, right? This one that's completely, it's not password protected. This is for anyone, anytime. You don't even have to be connected to the university. The other 2 are password protected. And one is for where you turn in anything that's graded, bonus work and homework. That's LANCAPO. Anything that's graded is going to be graded there. And the third one is Compass, and that's where we're using it as a grade book and for me to make announcements. So any questions so far about anything I've said? Okay, so now let's see. The last thing I want to talk about here is this R independent study. Now, R is a statistical computing language that's very powerful and that's free, so people are using it a lot in all sorts of fields. And it's, if you're going on in statistics, it's really, I think it's important to learn it. Now, At this stage, I think it's really an option. So this is an independent study that's a very rigorous course because basically there was a hole in the department. It's not teaching. Basically, I was asked to do this because there isn't, they just need some more R courses. So this is just an independent study that goes, but it's a lot of work. And I recommend it for anybody who's in computer science or has computer programming experience and enjoys programming. So you should take a look at this and look over the materials and probably look at the frequently asked questions. Like it's a lot of time. This is just data showing how much time students spend on the course. So it's rigorous and it's demanding. So maybe you want to save it for a semester where you have some free time. It goes along with this course. We have our own data analysis program. So if you go back to, first of all, if you want to sign up, the instructions are here. You just type in that CRN and you want to sign up for 2 credit hours. I'll let you out a little bit early today for people who want to ask me questions about anything I've said. So you can ask questions, but first just look at this. Now, are we going to learn R, or what data program are we going to learn here in Stat 200? Well, basically we have our own simple point and click data program that's basically just super easy, and it allows us to ask very interesting statistical questions and to act like scientists and really explore the data without any technological barriers or jargon. We just, from the get-go, there's no learning curve here. So we're going to offer that. And then we have the 2-hour R independent study, but we're also going to have bonus exercises for you. So let's look at how the grading's done. I can talk about the bonus exercises in R. So let's look at the grading. And the grading is 60% for the 3 exams, 20% for the 3 midterms, and 25% for the final, and 15% for the homework. Straight scale, do I curve? If I have to, if people don't do well in exams, I figure it's my fault, not yours. There's so many more of you than me. So yeah, I will curve, but usually I don't have to. I'll never curve down. It would be great if everybody in this class gets an A. I would be delighted. Okay, but it doesn't happen usually. So bonus points. Now there's a lot of extra credit for those of you who do have trouble with exams, or it's designed to help those who need it the most. So it's basically, you can get 100% if you do all the required work and not one bonus point, and you've got 100% in everything, well then you have 100% in the course. So, but of course that's rare. And so most people need these bonus points, and the lower, it's a scaled system by this formula right here. You can look at this, and it works out so that the lower your percentages on the required work, the more the bonus points will help you. And they're not silly, gratuitous bonus points. All these bonus points are for things I think will help people learn, that I would tell people to do anyway, but it's very hard to motivate people unless there's points attached. So these are all worthwhile things to do. They're not busy work. They're not just extra credit for no reason. So these are for the bonus review exercises, for the surveys I talked about, for the iClickers, because I really want to encourage you to come to class. Now, those online people don't get iClicker points, but I thought they're online and they might probably are more familiar. I just figured giving more for the bonus R exercises would make sense for the online group. And so that's worth 40 points for the same exercises rather than 20. Now these are simple exercises to familiarize yourself with R. They're using R as a command language, not as a program, not doing your own programming, but just learning commands so that you can do exactly the same problems that we do in class or do on the, using our point and click data program. So they're interesting exercises, but they're easy. And so I strongly recommend everybody do it. And then mostly, I strongly recommend everybody does this notebook. I can't think of, I'll talk about that in a moment, the notebook, because I'm going to switch to the document camera so that people online can look at the notebook. All right, so any questions? Probably the only thing I've left out is what else you need to buy besides the notebook, and that is a calculator. You absolutely need a calculator for the exams because you can't use your phone calculator or anything that connects to the internet. So you're going to have to bring a calculator to the exams. I don't care what kind it is. You can use a graphing calculator or a cheap calculator, whatever you want. You really don't need a graphing calculator. You can get by with a cheap one. But if you have one already, sure, that's fine. So any questions, any other things? Yes. How many attempts on the homework? Is that what you're going to say? Good question. The attempts on the homework, you can, vary according to the problem. So if there's a multiple choice problem with 3 possibilities, you'll probably have 1 or 2 attempts. I'm not going to give you 3 attempts for 3 possibilities, right? If it's a calculated problem, more. But you don't lose points with the attempts. So if you get it on your last attempt, if you get the right answer, it's the same as if you got it on your first. Any other questions? And there's a discussion board on LANCAPO where you can help each other and ask questions. And I strongly recommend that everybody use that. It's a great way we can see what you did and we can help you a lot. Yeah? Is there a piazza for this class? No. There's no piazza for this class. If some people want to get together and form your own discussion group, I strongly recommend you do that. I'd be happy to support that in any way I can. So if you want to get together and do that, that's great. Right now, people usually find just the discussion boards on LANCAPO is sufficient. But for the R independent study, people really do form those piazza study groups, and it's helped them a lot. Any other questions? All right, so I think it's time to go to the document camera. And I'll just mention a little bit about the notebook on the document camera. Okay, so this is the notebook that you need to get right here. It's the spring 2018 edition. And please don't get a used notebook that's already filled in. Why? Well, because what this notebook is a combined textbook, short textbook, and with lots and lots of examples to work out. So the examples are key. It's very difficult for people to understand without a lot of examples. So if you don't work out the examples together in class or while you're online watching, you're going to lose most of the pedagogical value of the course. There's nothing that replaces working with paper and pencil when it comes to math. You can draw pictures. There's many studies that show that it really develops pathways that are excellent for problem solving. So I think, especially for any kind of math course, and statistics is math, you absolutely need some kind of paper and pencil activities. And the exams that you take will also be on paper, will give you partial credit for the work that you show, and they'll be very similar to the examples that we work out here, which are also similar to the homework problems. So I think that it's just the best teaching tool that I've discovered, or that I've used ever. And a lot of people who use it, almost everybody who uses it, teachers and students, are agree. All right, so now, so everybody needs to buy it. Now, raise your hand if you don't have it right now. Okay, no problem, you know what to do. You buy it, and then you can watch, you can take notes, but you can watch the video again if you need to fill it in. if you fill this in, so the bonus points that I was talking about, those 20 bonus points will be awarded at the final if you have a notebook that's, 95% or 90, I'll explain which pages you don't have to fill in, but almost all complete. And if you miss a class, you just watch the video and complete it, right? Okay. So, ready to start chapter 1? Any questions before we do? Okay, so chapter 1 is about significance tests. So what is a significance test? You may have heard it referred to as a hypothesis test. These two are the same things. And it's basically, it's used when you want to make a decision based on the data. You want to make a decision under uncertainty, right? And most decisions we make are under uncertainty. We want to make some decision, and we have to weigh the different probabilities. So, it's one way to think of it is it has a very specific structure, though. It's when we want to determine whether some effect we see, some difference we see, like for example in the experiment that we're doing right now, do people learn better online or do they learn better in person, right? So we are collecting data. It's an ongoing experiment. We've been doing this. So we're measuring how well they learn by their performance at the end of the, by their performance on the exams and their overall performance in the class, what overall grade they get at the end. So now the question is, of course, whether, sometimes it's, let's say the online students, let's say the in-person people are doing better, okay? Let's say the in-person people did better. At the end of the semester, let's say overall you guys did better. Well, how do I know, how big a difference do I have to see before I can say that it was real? How can I tell whether it's a real difference due to the delivery, whether the fact that you're in the in-person, and maybe it's just chance variation, right? Maybe it's just that you would have done better even if you were in the online class. How do I know? So it's a statistical test to determine whether some difference we observe is real, meaning due to some particular cause, or just due to chance variation, the luck of the draw. And the way that it's structured is you set up what's called the null hypothesis, and it's abbreviated as H0, with a little 0 for null, nothing, no effect, the null hypothesis. And it's the hypothesis generally of no effect. That yes, we see some difference here in our sample, but actually it's a difference that wouldn't hold up. It's just due to chance. And so you can think of it, usually we want to reject this because it's the dull hypothesis and we want to show some actual effects. So you can think of it as the null-dull hypothesis of no effect. And this language of the population and the sample is, you'll see over and over and over again. The idea is that there's some, in our sample, like you guys at the end of the semester, in this particular sample, we might see some difference. But what we're really interested in is that going to hold up for the next class or for other people? Is that going to hold up in general, or is it just particular to this sample? So when we talk about the population, it's what we want to show that this extrapolates to a larger population or to an idealized population, that there is a real effect going on, and it's not just due to what we call sample variation. Just to this, it's not just true of this particular sample, but we can say, hey, take the online course or take the in-person, because you will learn better. That it's an effect that will hold up. So the null hypothesis is about the population parameter is a particular value. Like in this case, the population parameter would be the difference in this wider population between people who take online courses and people who take in-person courses, and that there's no difference in this wider population between, there's no difference in the learning outcomes. okay? And why we see a difference just now is just sampling variation. It's just due to chance, okay? So it's generally the hypothesis of no effect, that whatever we see in our sample is just due to luck, chance variation. So if we're testing a treatment, the null is that it didn't work. There's no difference. Like if you're testing a drug, the null would be there's no difference between the drug and a placebo, right? Then there's this alternative hypothesis, abbreviated by HA for alternative. And this is generally what you're trying to show. You're trying to show, hey, the treatment did work. And that there's some other reason besides chance that explains the sample data, right? It's the hypothesis that the effect we see is real and that it will extend. So the population parameter is not just this nothing value. It actually, there's something going on. And so it's, if we're testing a treatment, it's that the treatment worked. All right, so it's an argument by contradiction. I know this is review for many of you, but it still it's still important to go over, very important, because people have difficulty with this. So if you're seeing this for the first time, please be patient, and you're gonna see these same ideas. We're gonna work out a few examples, but you're gonna see them in very simple terms on the bonus review exercises. So please watch that. Okay, so you argue by contradiction. You assume that nothing is going on, right? So let's just continue with our example. So I'll say, I'm going to assume that it makes no difference whether you're signed up for the online or the in-person. The learning outcome would be the same. It makes no difference. So I set up a probability model, a box model. It's just a probability model, right? That's what that is, based on that null. So I want to translate this situation that we have into some kind of probability model. And then we'll ask if the results you found were very surprising, if the sample was randomly drawn from that box. So the simplest model might be for this experiment we're describing is to take all your overall averages that you get you're going to get a percent at the end of the semester. That'll translate into a grade, right? So I take that percent for all 300 people enrolled in the class, 150 online, 150 here in person. And let's say I took those 300 numbers and put them into a box. So we have a box, and inside the box are tickets, and on the ticket is written the outcome that we see at the end of the course, your overall percentage. All right? Now, if the null is true, right? If the null is true, and it doesn't matter which section you're in, then any random division of those 300 numbers, if I shook up the box and took out 150 of them and said they were the online and the rest were in person, and any random division of those is going to be, will be exactly like this particular class, right? Will be, not exact, what do I mean? That if the null is true and it has nothing to do with, it's just due to random variation, then the difference that I see at the end, let's say it was a 2% difference in the overall scores, well, that would just be one of the outcomes that happens when you divide these 300 scores into two groups, 150 each, and compute an average for each one. So let's say the average for one of them was 90%, the average for the other was 88%. That's what we actually got. And we'll see, is that 2% difference that we just saw, how likely is that to occur if we just put all your scores, all 300 of them, into this box, randomly divided it, took the average of each? How likely is it to get a 2% difference? I mean, if the difference that I actually saw in this class was, 90% versus 70%, we probably wouldn't need statistics to tell us that one of the methods is better. But we could still see how likely that 20% difference is. just by the luck of the draw. So what we're looking at is the sampling distribution of a particular test statistic. In this case, it would be the difference of the averages. Okay, does that make sense? And so that's what we're doing. That's why we have to, so that would be a probability model. And this is, I just jumped ahead, pick a statistic for which you'd expect the null and alternative hypothesis to give different values. The sample mean, that's what I just did. We'd pick that. We'd expect them to give different values if there really was a difference in the teaching methods. Now, and to see if it's outside the range that you get just by random sampling from the null box, you make a version of that statistic with a known sampling distribution, okay? For example, you change it to a z statistic because we know the sampling distribution of the mean divided by its standard error. We know with a big enough sample, that will follow a normal curve. And then we can look on the normal curve and see how likely, check how likely it would be to get our data's test statistic, to get a z-score that was, well outside, that was very unusual, right? Check how likely it would be to get our data's test statistic, or one even further from the null, if the null were true, and that's called the p-value. So if it's very low, the probability of getting a result, and the probability of getting like a 20% difference is going to be minute. We'd have a very, very small p-value, and that would be overwhelming evidence that there must be some real effect, and we would reject the null, okay? So how low is very low? Well, you've probably seen this convention of 5%. There's no particular reason for that. That's just very commonly used, or 1%. And another word for the p-value is called alpha, the significance level. All right, so questions so far? I know that's very abstract. We're going to do some examples. But first, what I want to do is do some real intuitive examples of looking at the costs and benefits of making, of what does this alpha mean, all right? So the significance level, you can think of it as the probability of, because you're going to reject, if you get a tiny little, of mistakenly rejecting the null when the null is true. It's called a type 1 error. And we set alpha to be low to keep the chances of making a type 1 error low. So think of it as a false alarm, okay? So let's go with this false alarm idea. So when the smoke alarm goes off and says there's a fire, when there's not one, that's a false alarm. That's like a type 1 error. So continuing with that analogy, we could think of some probability distribution. I'm not sure if it would be normal, but probably it wouldn't, but let's just draw. We're just trying to get an intuitive picture. A normal curve here. And when there's no fire, when the null is true, and the null is no effect, there's no fire, we have some quantitative measure on this axis of that smoke detectors, of the evidence of smoke. It could be the cloudiness of the air, right? The absorption of infrared light or something like that. That's going to, it's not 100% accurate because it's not only smoke that's going to cloud up the air, it could be dust and other things. And it's not always accurate. So when there's no fire, there still is a chance that this can go off, right? And when you're cooking, let's say you have, so this is when the null is true and there's no fire. We're going to set, there's a distribution here. And remember, we're making a decision under uncertainty. It's not perfect. So we're making some decision based on evidence. And let's say we make a decision somewhere, like let's say the more likely, this is a measure of how cloudy the air is or something, and that's usually because of smoke, but it could be because of other things, so there's uncertainty, and we decide to cut it off at some point, right? And that's when the null is true, okay? Let's wait a minute. We could just, let's say we decide to cut it off at the 5%. That would mean, let's just say, we cut it off here, and we think that, so that would be 5%, that little, and this would be the type 1 error right here. If we set it off, and that's 5% of the area of the curve, which would mean 5% of the time when the alarm goes off, there's no fire, and it's just annoying. Okay? And that's called alpha. And we set that. So let's write that. So let's make a little thing. That is alpha, and that is also, why is it the probability of a type 1 error? Why is it also? Because it's the probability, can you read that? Probability of a type 1 error. Because this is the distribution when the null is true, when there's no fire. The truth is there's no fire, so we are going to be wrong and making a mistake 5% of the time. If we set that to be 5%, we could set it higher or lower, okay? So it's a false alarm. Let's color code this like that. All right, but there's another type of mistake that we can make. And that's when the null is false. What if we don't reject the null when it's false? When the null is false, then we'd like our significance test to correctly reject the null, the false null. So a type 2 error, I'll code it in blue, happens when the null is false and yet the test fails to reject it. So it would be like if there was a real fire and the alarm failed to go off. That would be a worse error, right? So it's that the alarm fails to detect a fire that's really there. And so the probability of making that type 2 error is called beta. All right, and we want both types of errors to be low. But so let's think about how can I figure out what beta is? Well, let's say when there really is a fire along this same measurement here of whatever we're doing, infrared absorption or whatever, along this same axis here, when there really is a fire, right, it's going to have a different probability distribution. But there's uncertainty, so there's some overlap. So let's just draw another distribution. Like this. It's centered right there, let's say. So yeah, you're more likely for the fire to go off. But the probability of a type 2 error, can you see where it would be? It's going to be, we want the smoke, if we set our decision maker right here, here we're saying there's, from here, we're saying there's only a fire when we're on that side. But here, if it's anywhere to the left of this, we're going to say there's no fire. So we'd be making a mistake this percentage of the time. Because right here, this is when H0 is true, and this is when the alternative is true. So right here, this whole probability distribution is when the alternative is true, when there is a fire. So there is a fire, and if we set our decision making there, well, then this area right here is the probability, it's called beta, and it's the probability of making a type 2 error. And this would be a more serious error in this case because people could die, whereas the other one would only be annoying. So this would be a bad place to set it. So there's a trade-off that I want you to see. There's a probability of a type 2 error, and I want you to realize that this significance level, alpha, that we typically set at 5% is situation dependent. And in this situation, wouldn't you think that we should make it much bigger? So as to, because there's a trade-off. Unless we improve our detection system, if this is truly the uncertainty area, then if we lower, we'd like both alpha and beta to be as low as possible. But there's a trade-off. If we lower alpha, See how we make beta bigger? And if we raise alpha, we're going to make beta really small. And that's why, that's why smoke detector, that's usually how they're made, and that's why they go off so often, even when there's not a fire, because they want to make sure that the probability of reducing the probability of a type 2 error, which is much more serious. So it just depends on the situation. Now, what is the power of a test? The power of a test is defined as 1 minus beta. So if this is beta, all this area, all this is called the power. And it's equal to 100% or 1 minus beta. And this part to here is beta. So you can think of it as the power to detect the fire that's really there. You want high power. Okay, so that's the idea, the type 1 and type 2 errors and the trade-off. We can explore this a little bit more intuitively before we actually do some calculations. So let's do that. And sometimes this chart can help. So basically what you're doing is you have these two, you have the truth and you have our decision, right? And there's uncertainty. So we're going to be wrong. So we're making these probabilistic decisions, right? So when H naught is either true or it's false, right? When H naught is true, that means there's no effect. So think of it as nothing, negative. When H naught is false, there's an effect. There's a real effect. Think of it as positive. All right, that's the truth, right? Fire or no fire. Then we decide with a signal detection or something, or we set this signal. We decide, we make a decision. And we either decide what? We either reject this nothing effect and say there's a real effect, a positive, real effect, or we don't reject it and we just say nothing's going on. So we say there's no effect. Negative. So if you look at this, when H naught is true and nothing is going on, the only type of error you can make is called a false positive. To say when nothing's going on, you say, yes, we got a positive. And that is the type 1 error, the false alarm, the false positive. And the other type of when there really is a fire, when there really is a disease, when there really, like this is also true of diagnostic tests, testing for cancer or all sorts of, diagnostic tests. You either have it or you don't, or pregnancy test. And when you actually have the disease, the only type of mistake that you can get is a false negative, which says, no, you're fine. If you're testing blood for AIDS or whatever. So this is a false negative. All right, so that's the idea. In all these cases, we have to make a decision under uncertainty. This is important in almost all aspects of life. And we never know for certain what the real truth is. So whatever we decide, we're always going to run the risk of making type 1 or type 2 errors. And we have to understand the consequences of these errors. I know that people just say 5% for but that's not the way anybody who really cares about it or in real situations goes about it. So that's just sort of probably just for other reasons, that people just like conventions. So I don't want you to think be stuck to that 5%. All right. So so here we can get an intuitive type. That's what I'm giving you, an intuitive type picture. So in a randomized clinical trial, the null is the treatment didn't work. We could even extend this to assessing whether somebody's guilty or innocent of some crime. So in a jury trial, the null would be that the person's innocent. In a diagnostic test, the null would be that the person is healthy. No disease, the absence of disease. All right? And your homework is on a diagnostic test, okay? Now, so I think just to really cement it, we can look at something that comes up all the time here on campus, and that's detecting cheaters, right? So basically, we're deciding whether somebody is guilty or innocent of cheating. And boy, is it a bad detection system right now. There's no good way. I'm sure you know that people are accused of cheating when they're not, and people are getting away with cheating all the time. And nobody accuses them. So it's a very faulty detection system at the moment. And so the idea, so let's just look at it in the context of this, and we can look at the trade-off that I've personally experienced in dealing with this issue. Because of course I want to detect cheaters, but so let's look at this. So when H0 is true, there's going to, let's say this axis is some quantitative measure of the evidence accumulated when people, that we use to determine whether people cheat or not, which is what? We have proctors looking around and they see people's eyes wandering. Sometimes they'll think they see notes, out, or there's lots of different ways that people think that they see somebody cheating, all right? So, or just that they have similar answers on an exam and they're sitting next to each other, they're friends, and similar wrong answers, but etc. So there's some kind of, let's say there's some quantitative measure here. Again, this is just intuitive. I just want you to get the idea of the type 1 and type 2 errors. We're not doing calculations on this. All right? So we are on here. Here's the sampling distribution, let's say, when people are really innocent. Okay, so in other words, there's evidence against innocent people because they might just look around and people think their eyes are wandering around, and they might talk to their neighbor, but they're not talking about that. They're just mumbling or talking to themselves, and they get accused, right? They have this distribution. So let's say we set our cutoff right here, a certain amount of evidence. We'll say it's beyond a reasonable doubt. This is what's used in jury trial. You accumulate evidence, and you assume innocence. You assume this distribution, the null distribution, and if the evidence is beyond a reasonable doubt, at this point, then we decide they're guilty. But this right here, of course, is our type 1 error. So that's the probability that you're innocent, and it's alpha. Alpha, and it's the probability of a type 1 error. So these are the people who might get kicked out of the university or suffer severe consequences when they were really innocent. Of course, we want that to be low. But there's also the probability here of when the defendant is guilty. There's a lot of people who are very slick and they cheat very well, and I know this happens. They cheat from survey data because I've been doing this for years, and people say they do cheat on exams when anonymously report that they've cheated on an exam in college, and a lot of people are cheating and not getting caught. So this is the probability right here. By that same, they're very slick, their eyes don't wander, they look like they're innocent, right? So unless we improve our cheating detection system, this is, okay, so these are the people who let go. Well, I would feel terrible when the consequences were terribly severe. And if people got kicked out of the university, their careers were ruined. These are the innocent people, so you might want to lower that, right? You might want to say, okay, even though I really strongly suspect it, I'm not 100% sure. So you make it almost, this is what I did at first. You make it, when I first started teaching, almost so I could sleep at night, I just didn't want to think I'd convicted an innocent person. But now look what happens. Then the consequence of that was that people started cheating a lot because they knew that it took a lot to convict them, and it ruins the whole fabric of trust and of course. So that sucks too. So both of them are terrible. And thank God I came up with a better teaching detection system that separates these two curves by just giving exams that look identical but really aren't. And somewhere in them they're different. And then when in the worked out problems, you have different work, and it separates them so that it's almost impossible for people to have gotten that just by the luck of the draw. So that's the idea. Does everybody understand? Questions? All right. So this is just a summary of it, of what we talked about. And at the end of every chapter, I do summaries. And these are excellent for you to read on your own. I don't want to read them here. And I'll just fill in. You know that when the null is true, nothing's going on. The only thing you can make is a false positive. And when there is a real effect, of course, the only mistake that can be made here is a false negative. The rest of the page is just a review of what, in the nutshell, what we just discussed, and it's a great way to review for exams is to read the summaries, or even after, just to get a summary of the reasoning. All right, now we're ready to start chapter 2. I know people are getting tired, but just the way the course is structured, it starts off really fast. And so I can't really let you out early and be on track. The reason is because if you want to transfer to the other version, this is so confusing with the two versions. If you want to, I want to give you an opportunity to see what the homework's like, everything, to get into this course and see if it's not for you or is for you. And I want you to be able to transfer really quickly to the other section and vice versa. So if I delayed, it would be to your disadvantage. So that's why I'm starting off really fast, just because there are two courses. This 200 business is really not designed so well to have the same exact course number for two vastly different courses. So the other version is completely different and assumes you know no statistics at all from the start. So if this is over your head, I want you to get a chance to try it and see if it is. Okay. Now, all right. So what are we doing here? All right. Now we're going to look at, this is, in chapter 1, we looked at these okay, let's look at this. In chapter 1, what we just did is we looked at the simplest cases where there was only one alternative hypothesis, right? The person is guilty. There is a fire. The person has cancer, etc. There's only one alternative hypothesis. But usually the null is false under a whole range of alternative hypotheses. And we have to set a particular value for the alternative hypothesis to figure out the probability of a type 2 error. So how can we decide on any one particular alternative? For example, continuing with our analogy, how can I decide, this online versus in-person teaching method can be different in a whole range of ways. It could just make a few percent difference in your grade. It could make a huge 10% difference in your grade. It could make it could make a whole range of differences, maybe just 0.5%, but it's still the edge that would matter to people. So I have to pick one of those particular hypotheses in order to do these calculations, in order to figure out what the probability of a type 2 error is. All right? So, for example, if we're testing a flu vaccine, which is something that's really happens, it's actually very difficult to do. They have to think how big of a difference would matter to them, because it's very expensive to do this. Let's say usually 10% of the population gets the flu. How much of a reduction in that rate would matter to us? Would we care if the vaccine only brought down the incidence 0.5% to 9.5%? Well, if it's a mild flu, we probably wouldn't. It wouldn't be worth it. But what if it was a deadly flu? Then, 0.5% of 300 million Americans, right? If you're just talking about this nation just alone, that would be 150,000 people. And that would matter to us. That would be huge. We would save the lives of 150,000 people. So it just depends on the situation. Again, each situation is different. So, this is a point that I can't stress too much. Significance tests only tell you whether or not a difference is likely to be due to chance, not whether you care about it or it's important. Okay? Sometimes there's only one clear alternative hypothesis, so we have no choice to make. But way more often, when we choose an alternative hypothesis, we're choosing the difference we think is big enough to be important. So in the example that we're doing, if I thought what I think 0.5% difference is big enough to be important, probably not, but 1% maybe. So what I'd choose as my alternative would be the smallest difference that I cared about. I want to say one method's better than the other, and I wanted to make a difference that we actually in real life care about. Okay? So, So the idea, boy, I don't want to get so, this is more abstract stuff about how to do these calculations. Well, this probably, you're pretty advanced class. We can do this before we jump into an example. Usually I wouldn't, but I think maybe it will help. Some people like to see the outline of the roadmap of how we're going to solve this problem before we actually solve it. So let's look at it. All right, so to calculate the probability of a type 2 error, what we're going to do is draw these two curves, one when the null is true and one when the alternative is true. Now, it's going to be a specific chosen alternative, a particular alternative. We're going to choose. This sets the distance between these two curves. So this would be our hypothesized value, let's say the null value, in the example that we're doing with the online versus this would be like the difference between, this would be 0, that there's no difference between the two, right? So this would be the sampling distribution of the sample mean divided by its standard error of the difference, right? So this would be 0, there's no difference. And then when the alternative is true, well, I would pick a particular alternative. Maybe it would be, so this would be 0% difference, this could be 1% difference. And let's say I knew which direction it was going in, then I would put it over here. Let's just do the one-sided first. All right, so this is my specified value of the alternative in actual units that we're talking about, like exam scores or exam percentages. All right, and then this right here, what you do is your cutoff. And you say, okay, if I see evidence this far, then this might be 5% or whatever you set as your value. So this, again, is just what we've been doing. And this would be, if it was a two-sided, we'd maybe do 2.5% in this curve. But basically, whatever you decide to set as alpha is right here. And then, of course, this area here would then be our type 2 error. And to calculate that exactly, how would we do that? Well, we'd have to change these to z-scores, to standard units. And this is what we're going to do. We'd have to change values to standard units. So this would be, in standard, it would be 0, and it would be, in regular units, it would be 0 right in the middle in standard units, no different, right? And then we'd have to translate this right here, this distance here. How many standard deviations or standard errors is this away, right? So that would be a z-score for the whole distance here. So this would be our z-axis, which is just basically unit-free, standard units. Right? And this axis would be assuming the null is true. We'll just use the same axis here. All right, so that's what it would look like. And what we're going to do right now is we're going to just try to translate this in actual units into z-score. And you know how to do that. Basically it would be like the value minus the observed minus the expected over some standard error. And that's what we're doing right here. Another way to write this would be this is the same as if we just divided each side by the standard error, we'd get this distance, right? This is just this distance that we see, and we want to change it to a z-score. So we would divide it by its standard error, and that would give us this distance right here. All right? This is if you're unfamiliar with this, don't worry. What a z-score means, because it's in the bonus review exercises. So please don't get scared here if you don't know what I'm doing. But it's very simple to translate from. We're just trying to translate from actual units we're in into something called standard units. All right? So, and the way we do it is through something called the standard error. All right? So now, what we're doing here is, then what we're going to do is we have right here this beta, right? And this distance from here to here is going to be We have this alpha and this beta. So when we set this alpha, let's say we did it as 5% here, then we can get a z-score corresponding to that. And we're going to call that z alpha. All right, so we're just going to get a z-score corresponding to 5% in the tail, and that would be z alpha, that distance. And then when the null is true, right here, this right here, this little distance here, so maybe I should write it like this is z alpha from here to here, and this will be z beta. So we're going to divide this into two pieces, z alpha and z beta. So basically what we're going to do is solve for z beta, and once we get that, once we get the z-score, we can look it up and figure out the area. So on this curve, we're going to figure out that area. Once we know that z-score, how far it is from there, we can get a middle area and we can get that tail. So that's what we're going to do. So the roadmap is going to be, let's write it, the roadmap is what we're going to do first is we're going to calculate this standard error. And that's based on our standard deviation and our sample size. Okay, then the next thing we're going to do is we're going to, after we do that, we are going to get a distance, a z-score. We'll do this. We'll get this z-score, right? We'll just divide by by the standard error. So you can think of this as our observed minus our expected. Our expected hypothesis, under the null, and you can think of it like as an observed value minus an expected over some standard error is going to give you a z-score, right? And then the third thing is going to be, once we got that distance, we're just going to get z alpha and z beta, okay? So we'll find basically z beta. That's going to be the roadmap. All right. Z beta is going to just be this overall distance minus z alpha. So let's do it, and let's just start it, and work through it. So that's just the idea. Basically, translating from a. Okay. All right. So finally, an example, and hopefully this won't take too long. All right. Are you okay? Are you guys okay? I know it's a long lesson. All right, so I think my 2-year-old granddaughter, Talia, is a gifted statistician. Pretend I think she's really smart, and I want to test that claim by giving her 100 true-false stats questions. This is just a real simple example to see whether she's guessing or she really knows something, right? The null hypothesis is that she's just randomly guessing. Under the null, you'd expect her to be correct about 50% of the time, just by chance, right? If I give her 100 multiple choice questions, pretend she's a parrot or a dog or anything. She's just guessing. That's the null, is that she's just guessing, and she's just going to say yes or no randomly. So you'd expect her to be right 50% of the time. But I believe that she actually knows something and that she can answer correctly more often, let's say 60% of the time. I really think, I know she can't answer 90% of the time, but I think 60%, and I'll set that as my alternative, the minimum that I think I can detect, okay? So, following our roadmap here, the first thing is what? We're going to find the standard error. All right, so let's do that first. So, and we have to set up a box model, a probability model. I use this example because it translates so easily into a probability model. What is the null? The null, right here, under the null is that. The null is that she's going to get 50% correct. Now that's the way we intuitively think about it, but the way you would see it in statistical most notation would be what? Would be that this population mean, which is expressed with the Greek letter mu, the population is always expressed with Greek letters, and the sample is expressed with Roman letters. So this population mean, and we'll say the mean what? Under the null, so we call it mu under the null. The null is that it's equal to, and generally speaking, people use, this is a mean, so it would be, instead of 50%, we could express it as 0.5. That's the same thing. She'll get half the questions right. So that's how you would see it in ordinary statistical, statistical language. And the alternative is what? So the alternative hypothesis is that I think the percent correct should get, 60% or more right, is greater than or equal to 60%. And the way you'd express it would be what? Mu, the average alternative, is greater than or equal to 0.6. All right, so those are our null and our alternative. And it's one-sided because I'm trying to prove that she's smart, not that she's just unusual. If it was two-sided, it would be, I know she's just not guessing. She's either like brilliant, or else she just does everything the opposite and is just completely has the sign wrong or something. And gets everything wrong for some reason. But that isn't appropriate here. Okay, so now we translate it into a probability model. Well, it's the same thing, that's just a box model where we're just counting up how many, if she got them right or wrong, right? What percent she got right. So the null is that she's just guessing. It's like she's reaching into a box and just pulling out a yes or no ticket, right? Yes if she's correct, no if she's not. So if she's correct, I'll give her 1, and if she's not, I'll say 0, right? It's the same thing. And 50% of the box will be 1s, and 50% will be 0s. So she'll be drawing out of that box and putting the ticket back each time, drawing out, and for each question, that's what she's doing. Well, now we can calculate an expected value and a standard error for this. We'd expect her under this to get half of them right. And what would be the standard error? That's what we're trying to do here. Well, the standard error is, first it depends on the standard deviation of this box. Now, this is idealized. So we're going to say the standard deviation, we're going to call the standard deviation, we're going to call it sigma. That's for the population, standard deviation. That's the idealized box model population. And it's going to equal the square root of the percentage of 1s here of p times 1 minus p. So in this case, it would be the proportion 0.5 times 0.5, which is equal to 0.5. That's the standard deviation. And this is the formula on page 251 in your notes. So you can look on the back of the book for page 251, and you'll see that formula and what we're doing there. Okay? So now that's the standard deviation, but what are we doing here? We're looking at this variability. We expect her to get 50% right? Which as a z-score is 0, right here, right? We expect her, but there's some sampling error, and that depends on the spread in the box, which is 0.5, and it also depends on the sample size, right? We want to know the percentage. If she just picks one ticket, well, she could get them all right, or 2 tickets. She could get 2 1s. She could get 100% right. But the bigger the sample size, the lower the variability. And what I want to do is translate this 60% of the alternative into a z-score to see where it is on here. So I have to also realize that n is 100 right here. So that's n. So she's drawing from this box 100 times, because each time she answers a question, she draws from this box and puts it back. So now what we have to do is the standard error. That's what our first step is, and we're going to stop right after we get this. And the standard error is the standard deviation, we're calling it sigma, over the square root of n. That's for an average, right? We can change it to a percent in a minute, but let's just say for an average, okay? Square root of n, SD over square root of n. The bigger the sample, the less variability there's going to be. So that's 0.5 over the square root of 100. So that as a fraction is 0.0. As a decimal, as an average, is that, or 5% if you want to change it to a percent. So that's going to look like, that means that one standard error, z-scores measure how many standard errors. This is a standard error. 1, 2, 3. One standard error is 5% on here. So that's 55%. So here's where 60% would be, 65, and this is going to be 45, 40, and 35. And that would be -1, -2, and -3. So this right here is the standard error. And we're going to stop right there and can start there. So I can, you have at least 5 minutes. We'll do that. We'll start next time. So you'll be able to do the first homework problem on your assignment that's due Monday, but you're going to have to wait to do the second one till Thursday's lecture. But do the bonus review exercises.